Now we're going to look at using logs to solve exponential equations. Now, an exponential equation is where the pronumeral, or the unknown, the variable, is the exponent, or it's part of the exponent. So this is about the simplest type that you can get. So we could use the definition of a log here, but one of the easiest ways to do it is to say that if 3 to the power of x is equal to 5, then the log of 3 to the power of x must be equal to the log of 5 as well. And once we've got it into logs, then we can use one of the log laws, which you may need to just take for granted at this stage, but the log law that says that the exponent part x here can come down in front and multiply. So we've got x times the log of 3 is equal to the log of 5. So that means that x is the log of 5 divided by the log of 3. Now that's a calculator exercise, and we won't do that in this video. All I'll say is that that gives 1.465 to 3 decimal places. And if you want to check the accuracy of whether you're right, go to your calculator, do 3 to the power of 1.465, and you should get an answer that's fairly close to 5. This next one, the exponent's a little bit more complicated in this one, so the solution has to be a little bit more complicated. But we do have just a single exponent on this side that's not being multiplied by anything or anything else, so we can proceed to just take the log of both sides. And then we can use rule or law 3 of the log rules to then go and put that 2x take 1 in front of the log 2. And that's equal to log 45. So that means, and it was just a wise move to put 2x minus 1 in brackets there. It just saves a little bit of confusion. It's just a whole term. So that means that 2x minus 1 is equal to the log of 45 divided by the log of 2, because on the left-hand side of the equation we are multiplying by log 2, so if we move log 2 over, the opposite to multiplying by log 2 is dividing by log 2. So that means that 2x minus 1 is equal to, and that's a calculator exercise, and that comes to 5.492. So now we need to keep rearranging this. This is just a simple linear equation now. So we'll need to add 1 to both sides, so we'll get 2x on the left hand side is equal to 6.492 on the right hand side, and I'm running out of space, so over here we'll do, okay, to get x on its own, the opposite of timesing by 2 is dividing by 2, and that will give us 3.246. Okay, now this one's a lot more complicated because this is our sort of like our exponential bit, and we need that on its own before we can start taking the log of both sides. But over here it's been times by 5, and then 1 was taken away. So we need to get rid of the 1 and the 5, and in order to get 3 to the x on its own. So I'm going to have to add 1 to both sides here. So 5 lots of 3 to the power of x is 102. Now to get 3 to the x on its own, I'm going to need to do the opposite of multiplying by 5, which is divide both sides by 5. And that will come out at 20.4. Now we've got it down to just a simple exponential. I can I can take the log of both sides, so we know that the log of 3 to the x is equal to 20, my apologies, the log of, taking the log of both sides, 20.4, using the log laws, number 3 to be precise, we know that that exponent can come down in front, so it's now x log 3 is equal to the log of 20.4, so x is equal to the log of 20.4 divided by the log of 3, and if we do that on our calculator, we'll get something like 2.745. Okay, now the last question is one particular scenario. It appears in the PDFs and now in the video. It's something where it's a very typical usage of where you need to solve an exponential equation, and it's to do with finance and it's to do with simple interest, but it could also appear if you're doing something to do with annuities, for instance. So in this particular question, an investor deposits $40,000 into an account that compounds at 6% per annum. How long before this amount has doubled? And the compounding appears monthly. So basically, if the money's to double, the amount that we want to end up with is $80,000. The principal that we start with is $40,000. It's 1 plus, now I, it's 6% per annum, so that 6 needs to be divided by 12 to get it to per month. So that's 0.5%, and I probably should have left a percent sign there, per month, which as a decimal is 0.005. Okay, so this is 0.005 to the power of n. Just a couple of things we'll do in 2 steps. We can divide both sides by 40,000. That will give 2 is equal to, and 1 plus 0.005 is 1.005 to the power of n. So I've done a couple of steps there together, and that, just double check that. So now we've got an exponential equation that we want to find the value of n. N is the variable and it's an exponent. So we know that if we take the log of both sides, that the log of 2 is equal to the log of 1.005 to the power of n. The n can come down in front using log law 3. If you haven't had any experience with the log laws, you'll need to just accept that at this stage, and I'm not quite sure why I put a 2 there. It's the n will come down in front and it will be n log 1.005. So that means that n is equal to the log of 2 divided by the log of 1.005. And because I've run out of space coming down where the equal signs are all lined up, I'll come over here. So that means that now n is equal to, if you do that on your calculator, log 2 divided by log 1.005, you'll get this number, which is 138.975. So that means that money needs to be invested for a whole number of compounding periods to actually get the amount that you want. So we're going to have to take the answer to 139 months to get the amount that we're after. We'll be a few cents over, or maybe a few dollars over, but that's the reason you would round up. You would round up in every situation here, because you need to get to the end of that compounding period, which is a month in this example, to achieve the amount of money that you're setting out to achieve.